Good morning and welcome to this video on direct displacement based design of frame shear wall system. The first part of this topic is the theoretical background. We shall discuss on the theoretical sides of the procedure. Frame shear wall system is also known as the dual system. It consists of the frame elements, the beams and columns, and the shear wall elements placed appropriately in different locations of the plan. So for this I direct you to study this paper on direct displacement based design of frame shear wall structures by Sullivan et al., published in the Journal of Earthquake Engineering in 2006. This may be freely downloadable, you can check. So if you read the background paper, original paper, it will help you understanding the video. So here we are showing the frame shear wall system, the 3D building system. In the first figure, these are the walls. This is one wall. As a shadow, you should have another wall on the other side of the building of the same size, same thickness, and on the perpendicular direction also you require the shear wall, because the earthquake may come from any direction, mutually perpendicular directions of the plan. As shown in the plan here, this wall and this walls are the shadow of each other in the longer direction of the plan, and this wall and this wall are on the shorter direction of the plan. So when earthquake comes from left to right in this building, this long directional walls will get activated, because the shear wall takes the lateral force arising out of wind or earthquake or any other lateral force in its own plane. These two will remain silent in that case. When earthquake force comes from the direction towards the short direction of the building, then these short directional walls will get activated and they will take the lateral force. The shear wall should be generally put on the periphery of the plan of the building, symmetrically placed, and the number of walls can be more than one. Depending on the requirement, the number of walls you shall decide. The horizontal length of the wall is given by LW. This is the length of the wall. Vertical height is from the base to the top of building. Generally, it is not discontinued in between the height of the building. It is given up to the top of the building. And you have a thickness of the wall. Here we are showing the cross section of a wall. So cross section of wall, this is the horizontal dimension, which is called the length of the wall, LW. And you have the thickness of the wall here. Generally, 2 layers of steel will be put in the wall. So you have a mesh on one side, another mesh on the other side. In most cases, you can have some column-like element at the end of the wall, which is called boundary element. Boundary element increases the strength of the wall, increases the ductility of the wall, and gives stability to the wall. So this generally should be provided in the wall. So this much about the fundamentals of the walls. Now we go to the wall behavior. This we have discussed earlier also in some video, how the frame bends and how the wall bends, and frame shear wall interaction takes place. In the first diagram we are showing the frame only, beams and columns, and frame will generally bend in the shear mode. You see the convexity of the curve is on the right hand side of the drawing. So this is shear bending. Each fluid is shearing out by certain displacement, and that is the shear bending. On the other hand, when the cantilever is bending, it is actually a cantilever. The shear wall is a cantilever fixed at the base, and the cantilever width is very large, which is the length of the wall. So when it is bending, you see the convexity of the band is on the left hand side, unless the previous case. So this cantilever bending and this is shear bending, and both the walls and the frames are connected together monolithically in the building. So they will interact with each other. One will try to nullify the action of the other, something like that, because this curvature is on the right hand side and this curvature on the left hand direction, the convexity. So their actions are something like opposite to each other and they interact. So after final interaction, you may have a wall bending moment diagram like this, having a zero bending moment point here. This point is known as the inflection height or the height of inflection, where bending moment is 0. And you have a frame bending moment diagram here. It is obtained like this. If you put a unit load here, whatever bending moment it produces at the base, which will be nothing but that unit load multiplied by the height of the building. So it is a straight line changing. So this is taken as the frame bending moment diagram. This is the wall bending moment diagram, and there will be resultant bending moment diagram. So above the point of counterflexure, the frame is predominant in its action. So as if the frame is trying to pull the wall towards left. Below the point of counterflexure, the wall is predominant. So wall will try to pull the frame towards the right below this. So this is what is called frame shear wall interaction. Now wall takes the lateral force from earthquake or any other external actions. Frame takes predominantly the gravity load. So frame is generally designed for the vertical gravity load, live load and dead load. However, since frame is in monolithic construction with the wall, frame also will get deflected by the same amount as the wall gets deflected under lateral load. So if frame is not designed for some lateral action, it will simply break down. So to take care of this, what is done, the total base shear is divided into two parts. One part is taken as about 25% or 35% of the total base shear, and the frame is designed for this base shear. Wall may be designed for the remaining or for the whole of the base shear, but frame has to take this thing extra apart from the vertical load. Total base shear taken by the frame and base shear taken by the wall. The point of counterflexure of the wall is to be computed. You have to find it out for further calculations. Now, as you've seen in the frame buildings, the shape profile we had taken phi I. Here in the wall we shall not take shape profile, but we shall take displacement profile from the yield displacement of the walls. So this equation is like this: delta I equal to delta IY plus theta D minus phi Y wall edge inflection by 2 into HI. Delta I is the displacement of the whole system at the ith floor. Delta IY is the yield displacement of the wall at the ith floor level. Theta D is design drift. Phi YW is the yield curvature of the wall. HINF is the inflection height of the wall. HI is the height of ith story in the building. So some new terms are there here. We shall discuss all this. The yield displacement of the wall is given by two equations. So the wall is greater than the height of inflection, then this formula is valid. Phi YW H inflection into HI by 2 minus phi YW H inflection square by 6. But when the height of the floor is less than the height of inflection, then the second formula as given here will be applicable to get the yield displacement of the wall. Now, as we have discussed in the previous case with frame buildings, here also you have to convert the multiple degree of freedom system, the real building, to an equivalent single degree of freedom system, which is a single mass, single stiffness, single effective height and single effective damping, etc. So this conversion formulae are same as we have discussed in the previous case of the frame buildings. The design displacement is given by this formula. Mi is the mass in the ith floor, delta I is the displacement in the ith floor that we have discussed in the just immediately previous slide. M is the effective mass and delta D is the design displacement as given here. H is the effective height. Since all the parameters involved in the three equations are known to us in the beginning, so we can calculate all these equivalent single degree of freedom system properties. Now you have to consider the ductility of the frame and ductility of the wall. Ductility of the frame is given floor wise. So for the ith floor, this is the formula: delta I minus 1 hi minus hi minus 1, and whole thing is divided by theta yf. Theta yf is the yield curvature of the frame which we have encountered in the case of frame buildings earlier. So this is given by theta yf equal to 0.5 epsilon y lb by hb. Epsilon y is the yield strain of the rebar steel, lb is the length of the beam, hb is the depth of the beam. So you get as many number of mu fi as the number of stories in the building or number of floors in the building, and then you take the average of all this. So that will become the frame ductility mu f. Then you have to get the wall ductility. So formula is this: wall ductility mu w equal to 1 plus 1 by lp phi yw. Phi yw, we shall just take up the expression. The design displacement theta d and these factors known to us already. Now this LP is the length of the plastic hinge. Length of plastic hinge, we have discussed earlier in some video that plastic hinge can be either lumped or distributed. So LP, when it is distributed plasticity over a definite length, then length of plasticity is LP. It is given by these two formulae: 0.022 Fy dB. dB is the diameter of the bar in millimeter, and inflection height is involved here. And the second one considers the length of the wall, Lw. Out of these two, the smaller value is to be considered. And the phi yw, the yield curvature of the wall, which we have taken up in the previous slide also, is given by this simple expression 2 epsilon y by Lw. Lw is the horizontal length of the wall. Now we have to consider the damping in the system. So for that we have to find the damping in the frame, damping in the wall, and then finally system damping. So damping of the frame is given by this long expression, where mu f, the frame ductility, we have already calculated, and R is a new factor. It is called the post yield stiffness ratio, and another factor you are getting here, T trial, the trial effective time period. And the damping of the wall is given by this expression, similar, only the ductility of the wall is involved here, as was ductility of the frame involved in the previous formula. The trial effective time period, as is appearing here and here, is given by this expression, n by 6 into system ductility, that is mu es dot equivalent single degree of freedom system ductility of that is involved here. R is post yield stiffness ratio. What is this? We shall take up. And the finally damping of the whole system is given by this formula, mw xi w, m otf xi f divided by mw plus m otf. Mw is the moment in the base of the wall, xi w is the damping of the wall as given by this formula, MOTF is the overturning moment at the base of the building in the frame, xi f is the damping in the frame, and summation of these two. Now while calculating this moment of the wall, or overturning moment in the wall, or overturning moment in the frame, you need not take the actual forces. We take our relative forces and find out the values, and because it is a quotient here, division, those relative values will be working for our calculation purpose. For getting MOTF, we put a lateral force at the top of the building, which is equal to say 0.3 if you have taken 30% apportionment of the base shear to the frame. Okay, and MW, the moment at the base of the wall, is obtained by considering a unit load distribution over the height of the wall and taking the bending moments at base level. We shall take up all this in the numerical calculations. Now the post yield stiffness ratio, which is appearing here and here, is given like this. If you take the force deformation behavior of a system, then initially you have elastic condition, so say stiffness is K1. Here it is yielding. After yielding, the stiffness reduces. It is called stiffness degradation. So if you take the ratio of the K2 by K1, then this is called the post yield stiffness ratio. K2 by K1. Generally it will vary from say 0.5 to 0.05 to 0.1. That is 5 to 10% of the previous when it is a bilinear representation. Now you have to calculate total shear and the frame shear and the wall shear, etc. separately. So we have shown a building here. Each floor height is considered h for the sake of simplicity in our calculation. And at the top, lateral force is F1, then F2, then F3. Obviously, if I take summation of all this, I get the shear at different levels. So at the top level, the shear V1 equal to F1. What is the moment here at the top level? Because distance is 0 for the force F1, so moment is 0, M1 is 0. Now let us come to the second floor from the top, and force is F2, so V2 shear force equal to this F1 plus F2, or you can say V1 plus F2. What is the moment? Moment equal to this F1 into the height h, so F1 into h. Now come to the next floor downward, F3, force is F3, so V3 F1 plus F2 plus F3, which is nothing but V2 plus F3. So you can simply take the shear force at the upper floor and take the force in the current floor, and you get the shear force. If you take the moment at the third floor level, then you see moment equal to F1 is 2h, h into h plus F2 into single h, and this can be taken together, F1 plus F2 into h. Out of this 2h I have taken 1 here, and F1h I have taken separately. Split this into two parts. So F1 plus F2 is nothing but V2, so I can write V2 into h plus F1 into h is nothing but moment there, moment 2. So we are getting some generalized condition for finding those shear forces and moments. So shear force formula can be previous shear force plus current force, and bending moment formula can be previous shear into height plus previous moment. Previous means the just immediately upper floor. So if I follow up this formally, it will be easy to find out all the shears and forces in the frames and walls. Now wall moment also you have to calculate. So the principle we have just discussed in the previous slide, it can be written in a formula pattern like this. The overturning moment in the frame at the ith floor equal to overturning moment of the floor above this, just that we have discussed, plus shear force just above this floor into the height of the story. Height of story is simply hi plus 1 minus hi. That is the height of the story for the current story. So if I follow this pattern, I can calculate the overturning moment at any floor level I. Similarly, the wall moment that we discussed about, these are relative values, remember, not the true values. For the purpose of computation in the beginning, you don't require the real values. Finally, you shall calculate the real values. So this relative moment of the wall in the ith floor is equal to relative moment of the wall in the just immediately upper floor plus shear in the just upper floor into height of the story of the current story. So hi plus 1 minus hi. So following this almost similar formula, we can calculate the overturning moment in the frame and the wall moments. Now finally you have to calculate the base shear. This we have discussed at length in our discussion on the video on frame buildings. So obviously the base shear is given by Ke into delta D. Delta D is design displacement and K is the equivalent stiffness. Now remember, when we are discussing the direct displacement based design, we are considering only one parameter of the design objective, that is only theta D. We are going to satisfy only design drift in the building system. So remember this. Later on we shall go to another method where we shall be able to accommodate more than one parameters. So base shear is distributed. This also discussed in case of frame buildings. When the number of story in the building is less than or equal to 10, you can follow a simple formula. Fi equal to base shear into mi delta I divided by summation mi delta I. That is, the base shear is distributed in proportion to the product of mass and displacement of the current floor. If the number of story is more than 10, then there is some higher mode effect on the system, and that you cannot take into account just arbitrarily. So this is one way suggested in the literature to take the effect of the higher modes when the number of story is more than 10. So what we do, we distribute the 90% of the base shear by the similar formula as here, and 10% we keep aside. This formula Fi will give the forces at all levels including roof. So if I take this roof level force here from this formula and put that 10% base shear we kept aside and put it as the roof level force, then this indirectly takes into account the higher mode effect in the system. Let us further understand the frame BMD and SFD. The frame I have taken 0.30 force here. Why? Because suppose 30% of the base shear is to be carried by the frame. Then instead of taking 1 here, I take 0.3. And there are different floor levels available here. Total height of the building is h. So bending moment diagram will be this force 0.3 into h. So it is a triangular variation diagram, bending moment diagram. This for relative force 0.3 in the frame. Shear force diagram of the frame is a constant shear because you have given only one force here 0.3. So this is a rectangular shear force diagram. If you take the case of wall bending moment diagram is this, because we have seen it has a point of contraflexure here. The curvature changes at certain point. Keeping in the similarity with the bending moment diagram, shear force diagram also changes direction like this. This is the wall shear force diagram. Frame bending moment diagram we have seen in the previous diagram. So if you take the total bending moment diagram will be looking like this. So some portion will be cancelled due to the interaction of the wall and the frame, and some portion will be left out. Now you have to prepare certain tables for calculation. Those are like this: table for inflection height calculation, table for equivalent single degree of freedom system properties computation, table for frame ductility computation, table for the base shear distribution. Base shear that we calculate is distributed. In between, of course, other calculations are there, like how we calculate base shear, how we calculate other things. Those will be taken up. But these tables you require for computation. As the height of the building increases, the size of the table will increase, but the principle will remain same, and it can be carried out in the Excel sheets. Thank you very much. So in the next video, we shall take up the numerical application of the direct displacement based design for dual system. Please subscribe the channel, like and share the videos, and you can put your inquiries and comments in the comment box. I shall be glad to answer. Thank you.